So let's look at an example of going from a function to both a logic diagram and a truth table. So for the first thing is let's do a logic diagram. Oh, and real quick, let's say this just equals z. So we know our order of operations here. We do our nots before our ands, and then we'll do the parentheses, and the plus is the very last thing that we'll do, or in this case, our plus represents a logical OR. So we know that we're going to have a not, and let's just get our variables down here to start. So we've got a, and we're going to have b. And we've got an a not and a b not, so let's just make a not gate right here and right here. And this right here is an AND gate, and its inputs are A, not, and B. So we need to draw our AND gate first, right? So we've got our AND gate. And that input is going to be A not. So let's connect. So now we've got AN, and the output is A not. And we also need B. So eventually B is going to connect to this inverter, but I'm also going to take it and link it straight over here. So there we go. We've got A not and B. That's what this term is right here, right? A not and B. Now we need A and B not. So we get another AND gate here. And first let's drag down our A, and let's do a little jump there. So now I've got A connected to this AND gate, and let's also connect B. Alright, so we've got this term, and we've got this term. The last thing we need to do in order to get Z is we need to OR this term with this term. So what that means is we're going to put a big OR gate here, and we're going to drop these down. And that means our output is Z. So this is actually an exclusive OR gate. It's just kind of drawn using kind of our more fundamental gates, our nots, ands, and ORs. And now let's do our truth table. So we know we've got two inputs, and we know we have a standard order. And that order is 0, 0, 0, 1, 1, 0, 1, 1, right? This is just counting in binary, which is something we'll get into later. And we can label these, right? Normally we go in alphabetical order, A and B. And then we're going to have our output, which is Z. And we can actually work from the logic diagram or the equation that we have here. I'm going to work from the equation. So the nice thing is our ORs can kind of split things up, because if this is true, the output's a 1, or if this is true, the output's a 1. If they're both true, the output is still a 1. So the OR is a kind of a nice thing because it pieces up our expression so we can kind of look at it part by part to see where we're getting a 1. So this is an AND gate, and its output is a 1 if A is a 0 and B is a 1. A has to be a 0 since it's inverted, so that means if A is a 0, A not is a 1, and B has to be 1. So that means there's two 1s here. So there's two 1s here, our output will be a 1. So we've got A not, so right here, A is a 0, this section right here, A is a 0, and B is a 1. So this row right here. So we've got a 1 there. Now let's look at this next guy here. We've got A is a 1, B is a 0 in order for this AND gate to be a 1. So A has to be a 1, right? So we've got a 1 here. And B has to be 0 because as this 0 goes through this inverter, it turns into a 1. And we've got 2 1s at this AND gate. So we look for the section that A is a 1, so A is a 1 here, and B is a 0, so that's this row right here. So that means that any one of these guys is a 1, the output is a 1. Otherwise, it's a 0, right? The output is a 0. So that's how we get our, we've got our math expression, and then we've got a logic diagram, and we've also got our truth table. So being able to go from one of these to any other one of these is kind of an essential skill for any digital logic engineer. And working in all formats has its value.